Hey Ramblers, this video covers the material in our book corresponding to Chapter 1.3. We continue our discussion of a library of functions. We'll start off with looking at shifts and stretches. So if we know a function, how can we get a new function by changing some of the constants and shifting it vertically or horizontally, or stretching it, or compressing the original graph? After we've talked about that, we'll move on to this idea of composite functions. Now, composite functions are really important in calculus because when we get into derivatives and differentiating, we need to use different rules for composite functions. So it's really important that you have a concept of what they are so that you can recognize them later in the year. We'll then move on to symmetry. We'll talk about odd functions and even functions and their definition. And we'll wrap up the video talking about inverse functions, its definition, and the unfortunate notation associated with inverse functions. So I hope this video helps your understanding of calculus, and thanks for watching. There are two ways to manipulate a function on the coordinate plane using constants. The first is to manipulate it horizontally or vertically by changing the input of the function. The second is by changing the output, which will have the effect of stretching it or compressing it. What do I mean exactly? Well, if we're looking at a function y equals f of x, consider f the function. Of course, x will be our input, and our output is going to be y. Now, what happens when we change the input? We'll change it from y equals f of x to y equals f of x plus a. Now, what this is going to do is this is going to shift the graph to the left, which may be a little bit counterintuitive to you, that with the plus sign there we would expect it to go to the right. But here's why. Let's take a look at a table. Let's take a look at the familiar squaring function. So now, when I put in a -2, I get y equals 4. When I put in a -1, y is 1. 0, 1, and 4. But what happens if I change the input by some number, let's say x plus 1? Now I can put in an x value that is lower, and the function thinks that it's 1 higher. So for instance, when I plug in a -2, and the function thinks it's getting a -1, so the output is 1. When I plug in a -1, the function thinks it's getting 0, and so the output is 0. When I plug in a 0, the function thinks it's getting a 1, and so the output is 1. And when I put in a 1, the function thinks it's getting a 2, and so the output is a 4. So you can see what's happened is that my function has shifted to the left, because when I put in a -2, I get the output of what had been -1. So I managed to move the graph over to the left one position. Same thing happens when I add. If we had started out with the basic function y equals x squared, I can shift it in the positive direction by subtracting 2. Why is that? Because the inputs can now be 2 numbers larger, and I will get the output. The function thinks it's getting a smaller number. So for instance, when I put in a 2, the function thinks it's getting 0, and so the output is the corresponding output for 0. That's why it shifts in the opposite direction. Now, that is not the case when we talk about a vertical shift. So for horizontal shift, it goes in the opposite direction. This is because you are adding or subtracting your constant to the function after the function is acted upon the input. So for instance, let's take a look at our function here. We had y equals x squared, but then if we add 4 to it, we are going to shift our function value, x squared, we're going to add 4 to it. So now y equals 4 more than what you started with. If all of this makes sense, terrific. If not, just try to remember that if the constant is inside the parentheses, you move in the opposite direction of the sign. If the constant is outside, you move in the same direction. Okay, let's take a look at what happens when we multiply a function by a constant. So here we start out with the function y equals f of x. And we can stretch that function by multiplying f of x by a constant. So this should make sense. If you started out with y equals f of x and multiply that result by 3, then the y's are going to get bigger. And not surprisingly, you get this larger version of y equals f of x. Now, if you multiply by a negative number, you once again will stretch it. It will be bigger than your original if that number is greater than 1. But if it's negative, it will, I should say, if the absolute value of the number is greater than 1. But the negative sign will have the effect of flipping it over the x-axis. So you've now reflected your f of x over the x-axis and stretched it. So what had been your original f of x is now on the other side of the x-axis. So a couple things to remember. Given a function y equals f of x, if that number in front, a of a, is greater than 1, then the function is stretched. If that number in front is less than 1, then the function is compressed. And if that number in front is negative, then the graph will be flipped over the x-axis and stretched or compressed, depending on whether a was larger than 1 or less than 1. Okay, let's move on and look at some composite functions. Composite functions are functions within another function. So here, literally, g of x is inside of f of x and must be evaluated first before you can figure out the value of y. So let's take an example. Consider the function y equals 2x minus 3. That's made up of a function 2x minus 3 inside the absolute value function. So let's say that g of x is 2x minus 3 and f of x is our absolute value function. So we're going to evaluate g of x first and then plug that into the absolute value. Let's take, for instance, g of 1. When we plug 1 in for x, we get that g of 1 is equal to negative 1. So now f of negative 1 is going to equal the absolute value of negative 1, which is 1. So bringing it all together, f of g of negative 1 equals 1. It's important that you recognize that we had a function, which was 2x minus 3, inside another function, which was the absolute value. This is going to be a big step and an important concept for you in a couple of weeks when we start talking about differentiation. Okay, let's move on then. Okay, we'll run across two kinds of symmetries this year in calculus. The first is even symmetry, and the other one is odd symmetry. An even function is symmetrical across the y-axis. An odd function is symmetrical over the origin, which is a little harder to understand, but it means that things in the first quadrant will be reflected over and be the same as things in the third quadrant. Let's take a minute to look at the definition up here in the blue box. It's a little hard to understand, but just think of it this way. When you plug in an x to f of x, if it is the same as f of negative x, well then that has to be even, which is of course the first definition up there. On the other hand, if you are given f of x, that will equal the opposite when you plug in a negative value for x. So, for odd functions, the height, f of x, is negative when you put in a negative x. So take a look at the diagram above. When we have f of x, you see it's a positive height. But that same height is now negative when you plug in a negative x. Okay, let's move on and talk about inverses. Inverse operations are something you're already very familiar with. For instance, you know that plus and subtraction, adding and subtracting are inverse operations. Or from back in grammar school, dividing and multiplying were inverse operations. As you've gotten more sophisticated, you've learned some inverse operations like x squared has an inverse function, square root of x, or sine of x has an inverse operation, which is y equals arcsine of x. Now, we should note right away that there's a really unfortunate notation, and that is this -1 up in the exponent. That does not mean that this equals, because it doesn't, 1 over sine of x. That would be cosecant x, and that's different than arcsine. No, this -1 is an indication of an inverse function. So given f of x, the inverse function will be y equals the inverse of x, which has that -1 up in the exponent. However, that does not indicate reciprocal. Okay, let's take a look at some examples or look at one example of an inverse function. Okay, the tables above are examples of a inverse function. In 2005, Kenenisa Bekele, an Ethiopian runner, set the world record in the 10,000 meters. And the chart on the left shows us his time as a function of the distance. So if we look at 2,000 meter increments, we see that his times, not surprisingly, increased until he finished in the record time of 1,577 seconds. Now, if we were to look at the inverse of that function, the input would not be distance this time. The input would be seconds. So to find out how long it took him, or how far he went in 315.63 seconds, that would be 2,000 meters. Or you might ask, how far did he go in 629.98 seconds? And that would give you 4,000 meters. So you can set up functions with the input or an inverse function with the y as the input. But not all functions are invertible. An invertible function means that it has a inverse. Now, only those that pass the horizontal line test. Now, that should make some sense to you, because for a function to be a function, it must pass the vertical line test. And for an inverse to exist, it has to pass the horizontal line test. Let's take a look at the graph of an inverse function, and you'll see why. Let's take a look at a function that we're all pretty familiar with, that we studied last week, and that is y equals a to the x. And a can be any number that we've worked with. Well, we all remember that the inverse of an exponential is a log. And so the log function looks something like that, which would be y equals log base a of x. And you may notice that those two are a reflection over the line y equals x. So the point on y equals a to the x of 0, 1 is reflected over this line to the point 1, 0. And as you can see, just as the times in the 10,000 meter race, the x's and y's switch when we look at the graph. And that's what gives us the reflection. Now we can look at that same example with y equals x cubed. You may remember x cubed comes up out of the third quadrant, through the origin, and up into the first quadrant. Well, its inverse is y equals x to the 1/3. and that hug comes along through the origin, but rather than rising steeply, it hugs along the x-axis rather than the y-axis. All the while, these two functions are reflections of each other over this line, y equals x. Okay, a lot of information there, Ramblers. I hope you took good notes. We'll work on the exercises in class tomorrow. Thanks for watching.